Hello, what I'm going to do is review some Chapter 6 material, which is trig functions and graphs. So to give you a quick overview, we're going to do some conversions between degrees and radians, and then look at some arc length problems, area of a sector, basic sine, cosine kind of graph, and then we'll get into trig functions that have different amplitudes, periods, and then eventually the phase shift and vertical translations. And then we'll finish these with writing the equation of trig graphs. So a lot of material in this. I'll get going with the basic conversions, some of the easier stuff. So this first problem, these first three, what we're going to do is convert from degrees to radians. So what I'm going to want to do is have this conversion, which is going to be pi over 180. So since pi radians is 180 degrees, what would happen is my degrees on my numerator would essentially cancel with the degrees on the denominator, and my answer would be expressed in radians. So what I really can do is write this as 236 pi over 180, but I want to simplify the fraction part of this. So what I'm going to do is go to the calculator, and there's a nice little way of doing this. You just take 236 divided by 180, and you'll get an ugly decimal, but your calculator will do the work for you. You hit math, first option is frac, means I'm going to turn into a fraction, and this is going to express my fraction in lowest terms. You just have to remember to bring the pi over. So 59 over 45 is the reduced fraction, so 59 pi over 45 radians would be our answer. And we'll do the same thing for the next couple of these. The next one's a negative number, works the same way. I'm going to have my negative, and there's my pi, so I'll just fill in 112 over 180, and that's the part that, again, we're going to go to the calculator for. So I'm going to take 112 divided by 180. Calculator is going to turn this into a fraction for me in simplest form. So that's going to end up being 28 over 45. You just need to remember to bring down the negative sign of the pi. So negative 28 pi over 45. And again, the unit on that is radians. So radians is a unit just like degrees is. And then on the last one, 432, so we're going over 360 here on this last one. Same thing, I'm going to basically go to the calculator, take my 432, I'm going to divide by 180, and I'm going to convert this into a fraction. In lowest terms, I got 12 over 5. So once again, you just need to say, okay, this is 12 over 5, but I need to throw a pi on there. So 12 pi over 5 radians. Alright, so those are the first few of these. I have answers that are all expressed in terms of pi, which is what the directions wanted. And then for these ones, going backwards, same exact type of logic. I'm going to take my 3 pi over 5, which is in radians, except my conversion now is going to be 180 over pi. So instead of pi over 180, notice my degrees is going to be on top now, and my radians would essentially cancel out. So with these first couple examples, these are in terms of pi. Part C is not. So with these ones being in terms of pi, what's nice is your pi's cancel out. And what you really have to do is just take 3 times 180 divided by 5. And again, that's something that you can just do in the calculator. You can just type in 3 times 180 and throw my little divide by 5 here. And I get 108, and again, that's degrees. So taking 3 pi over 5 radians, convert it, there's my degrees. Same thing for the next one. So this is 5 pi over 8 radians. My conversion is 180 over pi. With this one, just the same as before, my pi's would cancel out. So in the calculator, I would take 180 times 5. And that's going to give me 900. And then I just have to divide by 8 for the denominator. And that's going to give me 112.5 degrees. Oops. 112.5 degrees. So directions say around the nearest hundredth. So this one just kind of chopped off at the 10th anyway. This last one we'll need to actually do the rounding. So this last one's different because 2.65 is not in terms of pi radians. Just to give you an idea of what pi radians means, we know that 1 pi is is for fact 180 degrees. So that 1 pi is approximately 3.14. So if this angle measure is 2.65 radians, it's not quite going to be a half circle, but an angle measure is going to probably be somewhere over here. So my guess is going to be 100 and something degrees. So in the calculator, before I do that, if I can get the setup, I would still take my 2.65 and have my conversion of 180 over pi. But what's different about this is there's no pi on my numerator to cancel. So when I do this problem, I'm going to take, do this over here. I'm going to take my 2.65 and multiply by parenthesis, and this is where I'm just going to throw my 180 divided by, and pi is second in the little up arrow here, and I'm going to get 151.83 degrees. So again, really crucial that you watch that you're putting the times here and then throwing that in parentheses. If you don't even put the times here, your calculator is going to multiply in a reverse order of operations, and you could get an incorrect answer. Alright, and now we're going to go on to arc length problems and area of a sector. So in this one, the radius of a circle is 6 centimeters. The arc length is 14 centimeters. We want to know the measure of the central angle. So in this type of problem, we're going to be talking about some sort of circle here where the length of an arc is 14. So I have no clue what that is. I know my radius, so this could be 14. My radius is 6 centimeters. And we want to know basically what the angle measure theta is, except it wants to know the angle measure in degrees. So the formula that I'm going to drop on you is arc length, which is the letter S, is equal to theta times r. But the catch is, theta is measured in radians. So what we're going to do is solve this equation for theta, but then we're going to use what we just did on this last side and just convert it right back into degrees. So it's essentially just solving a really easy one-step algebra equation and then using that conversion from the last example. So I'm going to do this the same exact way as far as the setup goes. I'm going to start off by saying 14 equals, and my radius is 6, and I'm going to bring my theta next to this, which we don't know. And I'm going to divide both sides by 6. So this is where I'm going to go to the calculator and say, okay, theta is equal to this number. And I think it comes out to about 2.3. So I'm going to take 14 divided by 6. So I get 2.3 repeated. And that's radians. So again, just keep in mind at the very end of this problem, we need to take this number and convert it into degrees. So what I'm really going to do is take that 2.3, just like we did this part 2c, we're going to multiply by 180 over pi, and we do have to include the pi in this calculation. So I'm going to take this value that's already in my calculator and multiply by my 180 divided by pi, and bam, 133.69 degrees. So a couple things is if you rounded this a little bit different, let's say you chop this decimal off as 2.33 and you try doing this equation, you would end up with, I think it's 133.5, and it just really depends on the rounding. But that's the general idea. Anything past that, I mean, as long as the directions say nearest hundredth, just round to the nearest hundredth. So this one then will go on to sector area, and the formula that we would use for that would be A equals 1/2 r squared times theta. Once again, theta is measured in radians. So suppose the area of a sector is 45 square inches, and the central angle is 206 degrees. We're going to find the radius of this circle. So the central angle in this case is 206. So what I don't want to do is put the 206 here. If I follow my arrow here, it had to be in radians. So this would be a problem. Don't want to do that. So what we first have to do in this problem is take the 206, just like we did the first problems, and convert that into radians. So that's the purpose of even going back to this first slide. What we did was we took any angle measure and converted it into pi radians, and that's exactly what I'm going to do here. I'm going to take the 206 in the calculator divided by 180. So I'll take 206 divided by 180, get this ugly fraction or ugly decimal, convert it into a fraction. I have 103 over 90. So again, that would be 103 pi over 90 radians. And that's what I want to substitute into my equation. So I'm going to throw that over here, substitute that in for theta, and now we're going to solve this. So these types of problems, I really like to break this up into a couple of steps, little by little. The first thing I'm going to do in this case is bring over this 1/2. You could divide by 1/2. I could also just multiply by 2. Numerically, it just makes sense to me. It's going to get rid of this fraction. 45 times 2 is 90. And I'm going to bring down the rest of this, just as it is. Nothing different. So now in my next step, I'm going to do the same thing that I did there to take care of my fraction. I'm actually going to just bring the 90 over by multiplying. And that's going to take care of this. Again, if 9 times 9 is 81, 90 times 90 would be 8100. And that's going to be equal to, now I have r squared times 103 pi. So this last step, or couple steps I should say, are really crucial. What you want to do in the calculator is divide by 103 pi. If you break this up and forget the parentheses, you'll be wrong. Sadly, your calculator would divide by 103 first and then multiply your answer by pi, and that's not right. What we need to do is take my 8100 and divide by parenthesis, and again, this is 103 and then pi. Close it, bam. So my radius squared is 25.03. So r squared equals 25.03, but we don't want r squared, we want r. So you have to take the square root at the very end of this. So I'm going to take the square root, I think it's going to come out to 5 even, yep. So even rounding the nearest hundredth, this will just end up as 5. So I will end up with 5, and my unit of measure is inches. So the radius of this circle is 5 inches. Alright, so now we'll get into the trig. Graphing a cosine function on the domain of negative 3 pi to 3 pi over 2. These are the types of problems where I just want to take a look at the unit circle. This is the point 1, 0. This would be 0, 1. This is negative 1, 0. And then 0, negative 1. So I like to just go through these basic sine and cosine graphs so you kind of see where the shape of the wave comes from. So what I'm doing in blue here is just identifying what these radian values are. So we have a full wave of cosine is going to end up being 2 pi radians. So what I'm going to do is break apart my waves here. I'm going to call this negative pi, I'm going to call this negative 2 pi, and all the way here at the end I'll call negative 3 pi, and I'm going to do the same thing on the other side. Alright. So how this will work is we're going to start first, and I want to figure out where cosine is at negative 3 pi. So if I'm going in the negative direction, here's negative 1 pi, there is negative 2 pi, so I'm going to go here, and this is negative 3 pi. And according to all of our coordinates, and this was in chapter 5, the cosine value is the x part of the coordinate. So cosine of negative 3 pi is negative 1. So that's going to be the lowest value of my trig function. That's going to be our min. So what I'm going to do is start with my 3 pi, or my negative 3 pi, and that's going to be at 0. And then basically we're going to continue this wave after this. I feel like that's the hard part. After this, if you just go clockwise with your wave, so as I'm moving my graph to the right, just take a look at what's going to happen. My next value, as I'm moving to the right, would increase by another pi over 2. So that would bring me back here, and the reason is the cosine coordinate is 0. If I go another little pi over 2, my cosine value is now 1. And then it's going to go back to 0. And then it's going to go to negative 1, and then so on and so forth. So this wave is really just going to break up. Alright, so I'm going to keep this pattern going up to 1, and then again, I'm going to go down to negative 1 at pi, and then we're going to stop here, which this is 1.5 pi's, and that's what 3 pi over 2 is. So I have all these little freckles on a page here, and I'm just going to connect the dots. So it's going to form a nice wave. Little bells, basically, little curves. And then we're going to stop here. So again, that's just basically a cosine wave. It's going to be infinite in both directions. We just graphed it on a very specific domain. Moving on to these next ones, this is where the amplitude will change, and then the period of the wave as well. So this first value is my going to represent, or I should say, the absolute value of this value of this first number is going to represent the highest or lowest point that my wave is going to go. In this case, it's going to go up to 2 instead of 1, and it'll go down to negative 2 instead of negative 1. The other thing that'll change is the period of the function won't be a standard 2 pi. In this case, we need to analyze this value, which I put a little 1 here, because the coefficient to theta is a value that we call k. And in this case, k is equal to 1 over 3. So there's a formula that we're going to use to calculate the period of a function. P equals, you take 2 pi over k. So my period is going to be 2 pi over 1 over 3. by dividing these fractions out, really I'm going to multiply by the reciprocal of this. So I'm going to take the 3 and really just multiply it to the numerator. And what that means is that my period of this function is going to be 6 pi. So what I'm going to do is drop a 6 pi all the way at the end of this graph. And I'm going to split this into 4 sections. So right in the middle of this, I'm going to call 3 pi then, because that's half of 6. And half of 3 would be 3 pi over 2. And then if I want to figure out what I'm counting by to get to this third value here, this is 3 pi over 2. This is 6 pi over 2, so this would be 9 pi over 2. So now I'm going to take a look at what type of function this is, which is sine. And every sine function, even before the phase shifts and everything, every sine function is going to cross at the origin, because sine of 0 is 0. The cosine of 0 would be 1, but again, that's a cosine function. This is sine. It's going to start at the origin, and what you're basically going to do is in this first dash, wherever this first dash ends up, you're going to go to your amplitude. So I'm going to go all the way up to 2, and then I just follow the wave of the function. From the positive 2, that's my max, so I'm going to go back down to 0, and then I'm going to go to this negative 2 value, and then back to 0. And all we're doing is tracing one full wave of sine. And that's it. Alright, next one then would be a cosine example. Again, I'm going to take the absolute value of this, which says, hey, my amplitude is 3. My k value in this case is 4. Again, it's the coefficient to theta. So if that doesn't mean the period is 4 pi, that just means my k value is. So if I want to find the period, I have to take 2 pi divided by the k value. So simplify this. It's going to simplify to pi over 2. And what that means is pi over 2 is going to be one full wave of this function. So I'm going to split that in half. Half of pi over 2 is going to be pi over 4, and half of that is going to be pi over 8. So again, to figure out this last value, you say, okay, this is 1 pi over 8, this is 2 pi over 8, so this is going to be 3 pi over 8. So this one is going to be a cosine graph, and it's going to go all the way up to 3 and all the way down to negative 3. So with the cosine functions, whatever this first value is going to be the start of your graph. So I'm going to start this graph at negative 3, and then I'm already at my min, so I really can only move up from here. So I can move up to 0, I can go up to 3, back down to 0, and then back down to negative 3. And again, it's just going to fill in a wave. So I'm going to just draw on that little curve. I feel like these ones are a little bit easier than the ones that have the phase shifts, but again, you'll have to do this type of problem to even do the phase shift ones. So that's what we end up with for that curve. This next problem, I'm going to give you the amplitude and period, and we're just going to work backwards. So we're going to write the equation of a cosine function that has an amplitude of negative 3 pi over 2, which that in itself is actually a typo. An amplitude cannot be a negative number, so that's my B. Realistically, the amplitude would be the absolute value of this. What I really meant to write in this is an A value, which is the first value of a trig function, and that would be the negative 3 pi over 2. So what that tells me is this function is going to start off as y equals negative 3 over 2 cosine, and then we need to figure out what the k value is. So I'm given that my period is equal to 4 pi, and we know p is equal to 2 pi over k. So I want to figure out k. I know what p is, so I'm going to substitute p here. So I'm going to say 4 pi is equal to 2 pi over k. And then I'm really just going to solve this. I can bring the k over to the left side by multiplying and then divide by the 4 pi. So basically these are going to flip-flop. K is going to be equal to 2 pi over 4 pi. The pi's are going to cancel out. 2 over 4 simplifies to 1/2. So that tells me what my k value is. So I can go back to my equation and write it as 1/2 theta. I could also have an equation that says y equals negative 3/2 cosine theta over 2. And these two things mean exactly the same thing. Okay, so really the only difficulty in this problem is figuring out what the k value is. And then again, the amplitude to be given is the first value, and I'm telling you that it's a cosine function. Now we get on to the tougher ones. Amplitude, period, phase shift, and a vertical translation of a function. So easy part of this is going to be my amplitude, which is 3. Another easy part is going to be my vertical translation. This graph is going to shift down 1. And that's what these first value and the third value would represent, would be your, again, absolute value of this is your amplitude, and then this phase shift, or I'm sorry, the vertical shift, -1 tells me that basically my curve could look like this, but with a shift of with a vertical shift of -1, it would take each of my values and just bring them down 1. Alright, so what we're going to do then, based off the inside parts of this function, is identify the period and the phase shift. So a couple values here. We're going to have p, we're going to have k, and now there's going to be another variable which is called c. So the period of the function is what we don't know right now. The k value, again, coefficient to theta, is 1/2, and my c value is the pi over 4. So what I'm going to do is use that formula that we did for period before, which says p is equal to 2 pi over k. So in this case, that would be 2 pi over 1/2. And again, the 2 is really just going to multiply by my numerator, so my period is going to be 4 pi. Okay, so now the last part is to get this phase shift. I'm going to do that over to the left. There's a formula for that as well. My phase shift of a function is equal to opposite c over k. So my c value is pi over 4, so I'm going to say negative pi over 4 over my k value, which was 1/2. So I'm going to do a little fraction magic here. My 4 is really going to just drop down and multiply to the denominator. My 2 is going to move up to the numerator. So the 2 gets multiplied by the negative pi to be negative 2 pi. The 4 is going to multiply by the 1 to be 4. And then I'm going to simplify this. 2 over 4 is 1/2. Bring the pi over. So negative pi over 2 is going to be my phase shift. So a lot of math in that type of problem. Again, basically my advice would be to just sort out from the very beginning the p, k, and c values. Figure out what your period is. Again, that's going to go here, and then you're following the formula for the phase shift. I feel like the difficult part of this problem is really just how to simplify fractions. So the last two that we're going to do then, I guess with these types of problems, are going to be to try to graph one. And again, these are going to have a phase shift and a vertical translation. So I'm going to do a couple of things here off to the side first, state what my amplitude is, which again, that's going to be the absolute value of -2, which is +2. I know that my k value here is 2. It says 2 theta, so that's the coefficient. And my c value is pi over 2. Okay, vertical translation, I can also just get that out of the way. That's going to be saying I'm going to go up 1. So what I'm going to do is first figure out what my period of this function is. I'm going to take 2 pi divided by my k value, which is 2. And I'm going to end up with a period of pi. So one full period of this wave is at pi. Half of it would be pi over 2. Half of the half is going to be pi over 4. And then this value, again, this is 1 pi over 4, 2 pi over 4. So this is 3 pi over 4. So it's a cosine wave. What I'm going to first do is say, okay, let's figure out what the basic sketch of this graph would look like. Oops. Before I put these dashes in here, what I'm even going to do is just get the vertical translation out of the way. So I'm going to draw this thing right at a shift of up 1. And this thing is going to be referred to as the midline. And that just basically says, okay, you know what? I'm going to make my cosine graph based off of this point. Okay, so I know my amplitude is 2. So I'm going to go 2 units above that and 2 units below that. So what I want you to do is look at this y-axis now. This coordinate right here where my cursor is at 0. My low value is going to be at -1, and my high value is going to be all the way up here, which is technically going to be at 3. So we're going to start, because this is a cosine function, what I'm going to do is make a sketch of this graph before I even take my phase shift into consideration. So I'm going to graph this function. Because it's cosine, I need to start at the value of the minimum of the amplitude. A lot of math words. I'm going to start down here. And then again, you're going to just move to 0. I'm going to move up to my max. I'm going to go back to 0. And then I'm going to go down to my negative. So what I'm going to do is draw in the fact that this is what my curve would look like, except I have a phase shift. That pi over 2 is going to shift my graph. And we need to figure out what that's going to look like. So phase shift equals, you take, again, negative c, or opposite c over k. So I'm going to take opposite pi over 2 over my k value, which was 2. And this is going to simplify this 2 drop to the denominator. This means that my function is going to shift to the left pi over 4. I know this is to the left because this is negative. So what that means I'm going to do is take each of these 5 points and just shift them to the left an entire pi over 4. Since we were counting by pi over 4s, this is really easy because that means this distance where my cursor is highlighting is pi over 4, and we're just shifting every point to the left pi over 4. So I'm taking each of my coordinates and just moving them to the left, and then I can draw in this wave. And again, this one that's going in, this reddish orange, is going to represent what my actual graph would be. So the blue curve represents the graph before the phase shift. The red curve is the actual graph of this function with the phase shift and the vertical translation taken into consideration. So there's a lot of work to get these graphs. We'll do one more of those. This time it's going to be a sine function. Good news is at least the amplitude is just 1, so no big fancy stretch here. But again, we're going to start also with a midline value, or a vertical translation that's going to shift down 2 units. So off to the side, I'm going to list that my vertical translation is going to shift this down 2. I'm going to have a k value in this case of 1/4. My c value is pi over 4. So first thing I want to do, let's figure out the period of this function. You take 2 pi over k. Alright, using my little fraction trick, my 4 is going to jump upstairs, and 2 pi times the 4 means my period is now 8 pi. So I'm going to label this appropriately. This is 8 pi. This would be half of 8, which is 4. This would be half of 4, which is 2. And then 2, 4, this is going to be 6 pi. So the next thing I'm going to do is draw on my midline. Again, we're going to shift down 2 units. I'm going to draw a line here, which is basically my new home of the x-axis. Okay, so this is just shifting my curve around that. And what I'm going to do is draw in this sine curve. Again, my amplitude is going up 1 and down 1. So because it's sine, though, you need to start at the point that is, quote, 0, 0. And again, I'm going to go up to 2. And then I'm going to go to this 0 here. I'm going to go down, go up to 1, and then to 0, and then to -1, and then back to 1. So make it dashed. This is what my curve would look like, except again, now I'm going to apply a phase shift. Okay, so my phase shift is equal to opposite c over k. So in this case, that's going to be negative pi over 4 over 1/4, which your 4s are really going to cancel because this one's going to go up top and this one's going to go down here. So what I really have is negative 4 pi over 4, which is just negative pi. So what this tells me is each of my points are going to shift to the left 1 pi. What you need to pay attention to on this is that I was counting by 2 pi. So I'm going to have to go and basically move each of these points to the left about. For this first point, it's going to go to about here, which is 1 pi. This point would end up here. And if you can just follow my green dots then, these are going to make up where my values of my new curve would be. And my last one, again, would be about right here. So this curve that I'm drawing in green is our graph. Okay, so that one, again, takes into consideration the phase shift. And again, these are difficult problems. So what I like to do is just kind of break it down into identifying the key characteristics off to the side. I drew in my period. I graphed the dotted function just like we did these ones before. The first 2 that we did I thought were easier to manage. And then we ended up making that function in a dashed line, and then we took the phase shift into consideration. So now these last 2, we're just going to write the equation of these graphs. These ones don't have any phase shifts or vertical translations. What I really want to do is just basically identify are these sine or cosine curves, follow a period, get the k value, that whole thing. So in this first example, notice that it does not cross at the origin. That first indicates that it's going to be a cosine function. My amplitude of this, or my starting value, is at +2, so I'm going to throw that value here. And really what I need to do is just follow one full wave and see what my period ends up being. In this case, my period is 4 pi. Now, again, that does not mean I'm going to put 4 theta here. That's not a k value. We need to figure out the k value. That's the only really part of work that you need to do here. So p equals 2 pi over k. I'm going to substitute 4 pi into the left side of this equation. I think we had one like this before, where the k and the 4 pi really could just flip around. And what I'm going to really end up with at the end of the day is 2 pi over 4 pi, which is 1/2. So that's going to be the k value, which I had expressed this before as well. We can just write as theta over 2. So I really flew through that problem. But again, you're looking at the fact that it's cosine because it doesn't cross at the origin. My amplitude is 2. That's where the 2 comes from. And then again, all this work in green. The hard part of this is just knowing how to manipulate fractions. And that's what got me my k value. And then the last one. This one does cross at the origin. That's going to be an indicator that it's going to be a sine function. Look at the height of this graph, or how low it goes, which looks like it's about 1/2. So since it goes positive first, that's really important. So notice this graph goes from 0 and it's increasing after the origin. That indicates that my half is going to be positive. So with this type of problem, I need to figure out where one full wave is, and that's what this period is. So my period for this problem is pi. So I'm going to say pi is equal to 2 pi over k. I'm going to do my little flippity flop here with the k and the pi. So 2 pi over pi simplifies to 2. So that is my coefficient of theta. Again, that is my k value. So this is an insane amount of material. Tried to whip through this as fast as I could, but also be thorough. So again, from the top, let me just recap all this madness. We did degree radian conversions. Felt like a long time ago. And then we went radians to degrees. We did arc length, area of a sector. Talked about graphing a cosine function. We did a graph of sine and cosine with a phase shift, with an amplitude and period change. We wrote an equation of one of those, and then we started analyzing the harder problems that took into consideration phase shift and vertical translations, and then we finished off with these graphs of trig functions.